Today I'm going to talk about influence in Go and a scientific approach to understanding and calculating influence. What is influence? Influence is simply the effect of a stone or a group of stones on other stones or upon empty points on the board. Influence helps us to evaluate non-final positions before the end of the game. Unlike, say, in chess, where we have values of particular features that we can then use to make our estimates of the value of a position as a whole, we do not have such ready-made values in Go. In fact, the only way really to get a precise estimate of a position is to work out the game tree with different sides moving first. And of course, that's what we want to avoid with an influence function. We'd like just to get an estimate that doesn't require us to play things out. In his probably first computer program to play Go, Zobrist had an influence function. This is some 4 decades ago. But since then, computer programmers and others who might be interested in influence did not come to a consensus as to how to calculate influence. And in fact, modern computer programs, the Monte Carlo programs, play positions out to the end when they can just simply evaluate the end of the game score, so they don't have to worry about the influence function. However, human beings generally are not able to do that, and so it may be useful for us to learn how to use influence and to estimate the value of positions. Well, I call my approach a scientific approach because I take the metaphor of the laboratory, and instead of trying to make a guess at how to calculate the influence over the whole board, I start with small positions where I can make precise evaluations and then generalize from there. Welcome to the lab. This diagram is pretty familiar. It appears in probably every Yoset book in the world, or most of them in any event. This is something where we know the values for each of these corridors. They're easy to calculate. The top corridor has a value of 1/2 for black. That's whether we're using area scoring or territory scoring. The second corridor has a value of 1 1/4. The third, a value of 2 1/8. The fourth, a value of 3 1/16. Now the question then is, can we go further than simply knowing the value of the corridor as a whole? Can we assign values to each point in the corridor? If we can do that, then we can see how influence radiates out from the stones. We can do so by assigning a probabilistic meaning or interpretation to Sente and Gote. That is to say, if the position is Gote, 50% of the time white will play there, and 50% of the time black will play there. On the other hand, if the position is Sente, then the player with Sente, we figure, will play there all of the time. Now in a real game, of course, we know that sometimes people play the reverse Sente, and that does not happen. However, when we're evaluating positions, or estimating the value of a position, then we assume that the player with Sente gets the Sente play in 100% of the time. Doing so then allows us to assign values to each specific point on the board. as long as we can evaluate the position. When we do that, we get these values for particular points in the corridors. Now these values hold whether we're doing area scoring or territory scoring. It's sort of obvious and easy to see in terms of territory scoring. The top corridor, if black plays, the endpoint will belong to black, whereas if white plays, it won't. But it comes to the same thing with area scoring, because if white plays, then there's a 50-50 chance that white or black will play the next point, so we count its value as 0, just as we do with territory scoring. Then if we look at the next corridor, we see that there's a 3/4 chance that black will be able to prevent white from making both plays in the corridor. 1/4 chance that white will get both plays in. So the value at the end of the corridor is 3/4. The value in front of that is 1/2. And as we see, this pattern repeats regularly for every one of the corridors and gives the correct value for the corridor as a whole. How then to derive these values? Well, one approach, and the one that I adopted, is to figure the black influence and to figure the white influence and take the difference between the two. If we do that, then assigning a value of 1 to each point in the corridor for the black influence makes sense, and that's what this shows. Of course, this doesn't mean that there's a probability of 1 that black gets these points. It's just the value of the influence function. We get a white influence function, which is fairly obvious and regular. It starts at 1, adjacent to the stone intruding into the ur next to it, and then the next point gets a value of 1/2. The next point down a value of 1/4, then 1/8, 1/16, and so on. It is quite regular. And then we add them together, or the difference from them in the black influence function, to get the net influence. We get the points that we figured before by taking the probabilities of playing Gote. So far, so good. Next, we take a look at the open corridors, open at both ends, to see how we might combine the influence of different stones. Now, we still have the black influence as 1, but what about the white influence? Well, let's see what the values are for the particular points. We figure it the same way as we figured for a closed corridor. And that gives us a value of 1/4 for each of the center points, depending upon which way the point is made, if it eventually is made. Again, we don't bother with showing the black influence because we already know that we figure it as 1 point for each point in the corridor. If we add up the white influence from the right and the white influence from the left, we get these figures: 9/8, 3/4, 3/4, and 9/8. You see, the problem is that the 9/8 are too large. If we subtract 1 from that, we get 1/8 point in each corner for white instead of 0, which is what we want. If we cap the values at 1, we've added up, then this gives us the right answer. Subtracting these values from 1 gives us 0, 1/4, 1/4, and 0. What about Sente? Now here we have 2 corridors where Sente is involved, and the top corridor is a Sente, and then the bottom is a delayed Sente. White moves, and then the next move for white is Sente. This slide shows the area values for the Sente positions here. We're using area values because this is at an AGA-sponsored event. Note that red 1 there, where the white gets to play the Sente play. That will show up in the influence for white in the next slide. So now we get a value of 2 where the Sente stone is played in the upper corridor. That means that the white influence Sente with Sente is not capped at 1. It is capped at 2. And down below, we see that that value of the similar point is, of the Sente point, is only 1 because the 2 points are shared. The whole influence in the corridor is only 2 points, and it's shared between the first 2. Now this is true of area scoring. It is not true of territory scoring. With territory scoring, you can cap even Sente values of influence. You can cap them at 1 point. The next slide shows that. This slide shows the white influence when we use territory scoring. Instead of there being 2 points where the Sente stone is played, those 2 points are shared between that point and the one next to it. In territory scoring, of course, it doesn't matter that white plays on 1 point and black plays on the other. Neither are going to become territory, but it does matter for area scoring. Similarly, the 1/2 points shared between the 2 points in the second line. So what it comes down to is that the total influence is the same. It's only a question of which point we assign the values to, depending on territory scoring or area scoring. So we see, as we might have expected, that the total influence is the same, whether we're using area scoring or territory scoring. This makes sense because, as we know, generally the difference between area scoring or territory scoring is within 1 point. The differences larger than 1 point arise because of other differences between the particular rule sets. So while the total influence is the same, as we see with the Sente examples, the values, the influence values for specific points may differ. The next question that comes up in corridors concerns the influence, if any, of stones which are neither fully alive nor fully dead. The white stone by itself in the corridor is half live, half dead. White to play can connect and save the stone. Black to play can cut it off. What influence, if any, does it exert? We configure the values as before. The stone is worth 0 by half the time it will, by area scoring, half the time it will be captured, half the time it won't. And then the rest of the corridor on the other side beyond the stone looks familiar. Then this gives us white influence, again emanating from the stone, of 1/2, 1/4, and 1/8 instead of the usual 1, 1/2, and 1/4. That means then that the half dead stone, the half live stone, exerts half the influence of the not only living but immortal stone at the end of the corridor. Here let's look at a stone that is 3/4 dead. That is, the second stone was the second white stone in the corridor, going from right to left. As we might expect, it's not going to exert very much influence at all. Let's take a look at the values. And as we might expect, the stone which is only 1/4 alive exerts only 1/4 of the influence going down the corridor. So we see that as a general rule, the degree of influence which a stone radiates is proportional to the degree to which it is alive. Here I've indicated a two-line corridor with indeterminate length. That's what the little dots on the left are meant to indicate. What we see in such situations, if the influence is radiated far enough, that eventually it drops by half with each point of distance that it goes. You can see this effect in the lower line, where it starts off between the first and second points. The influence remains the same, but then it begins to drop off, as it does in the line above. This effect is quite general. As a general rule, then, if influence extends far enough, eventually we'll reach a point where it drops by half with each point in the case of Gote, or in the case of Sente it stops abruptly, because the Sente play is made, and then once the Sente is answered, there is no more influence beyond that point. So let us now turn to influence on a real board, albeit a small one, the 3x3. In corridors and small rooms, the stones that frame the corridors or rooms are considered to be immortal. Any plays inside the rooms or corridors have no effect on the life or death of these stones. On a real board, of course, we may have stones that are alive, but are vulnerable to attack and threatened with death. What is influence like, then, in a real situation where stones are not quite so strong, and therefore their influence might not be quite so great? There we have the center stone, which of course dominates the whole board. But if we do the corridor values that we already have, we see that the territory values add up to 6. And then, of course, since we're doing area scoring, the stone in the middle is worth 1 point, which is only 7 points, 2 points off from what we know it would be. Next, let's take a look at the side stone and see how it is evaluated using the same method that we used for corridors. Here are the corridor values that we figure for the side stone. 3 points worth 1, 3 worth 1.5, that's 4.5 points. Another half point for the 2 corners is 5 points, and 1 more point is 6 points. Next, let's take a look at the cornerstone, which looks really very weak. Let's add the values for the cornerstone. Counting the stone itself, we have 3 points that are valued at 1, that's 3 points. 3 points valued at a half, brings us up to 4.5 points. 2 points valued at a quarter, that brings us to 5 points. And 1 point valued at 1/8, so that's 5 1/8 points. Now, it's probably obvious that using these values, the cornerstone is way overvalued, even though the center stone is somewhat undervalued. And the side stone is also overvalued, as we shall see. Center stone is worth 9 points, as we mentioned. The side stone is worth 3 points, and I'll get around to showing that later. The cornerstone is worth 0. It is dead. So the corridor's values are wrong, even though we were able to work them out. In one situation, when we get to an actual board, they don't work. Can we then, however, take these features, these values for a center stone, a side stone, and a cornerstone, and add them together like we do for values of chess pieces? Well, if we have all 4 of the cornerstones on the board, each one is worth 0, and all 4 of them are worth 0. So far, so good. Because white plays in the middle, white will take the whole board. Similarly for black. And again, it's fairly easy to work out that 2 of the side stones, both opposite or adjacent, are worth 6 points. 3 of the side stones are worth 9 points. So that's exactly right. This is looking pretty good. 4 of the stones add up to 12 points. Well, obviously, there are only 9 points on the board. But if we follow the heuristic that we did with corridors and cap the values, then we would obviously cap the values at 9 points, and the fact that they add up to 12 is no particular problem. Now, I mentioned that I was going to show why the cornerstone, the side stone rather, is worth 3 points. Why the single side stone is worth 3 points. Black to play could take the whole board for a score of +9, gaining 6 points. But white 1 in the center moves to a value of -3, also gaining 6 points. White threatens to make another play, taking the whole board for a score of -9. But black can take the 6 points back with the clamp at 2, returning to a score of +3. 3 and 4 are actually Miai. Whoever plays first threatens to take the whole board, but the opponent can reply and prevent that. The end result is 5 points of area for black and 2 points for white. Now let's look at this position where each player has a stone on the board. It could be reached, for instance, if black started off playing on the side and white replied in the center. We already know that the value of this position is -3. But if we add up the features, we get -9 points for the center white stone plus 3 points for the black stone on the side. And that gives us a value of -6. And that's 3 points off. That's a rather large error considering that there are only 9 points on the whole board. However, values or errors that large are not atypical. So it turns out when we take the approach of chess and add up the values of individual features, we get fairly large errors. Positions with few stones, even if they have equal or nearly equal number of stones on each side, can have errors greater than 3 points. Of course, that's not true for all such positions, but it's difficult to reduce the errors to less than 3 points. What we would have to do is to add more features and special situations, and it becomes more complicated. Instead of doing that, let's go back and try the approach of corridors again with some modifications. So now let's figure the corridor values of white in this position. On each side we have 2 points, 1 plus 2 halves, and then 1 point for the other point adjacent to the stone and 1 point for the center stone. That gives us a total of 6 points. This time, instead of calculating the black stone at full strength, let's consider it as half dead, which in fact it is. White could kill it in one move. And therefore it generates only half of influence. We count the stone itself as only 1/2 point, and each point to the side is 1/2 point. Then 2 quarter points make a total of 2 points. 2 of the 1/8 points bring us up to 2 1/4. Add a 16th, we get 2 5/16. Subtract that from the white influence of 6. That gives us 3 11/16. Well, that's an error of 11/16, but it's still less than 1 point and much better than the error that we got from the features approach. This position has a value of +3, as we have seen. And yet if we take the chess-style features approach, the center stone would count as 9 points for white, -9, plus 3 points for each of the black stones, which would give us a sum of -3. That's 6 whole points off, so that's way off. Instead, let's take a look at what happens if we evaluate using the approach that we used in corridors. The white influence, we get 2 points on either side, plus 1 in the middle is 5 points for white. The first thing to note when we're considering the influence of the black stones is that with 2 of them on the board, white no longer threatens to kill either one with a single play, and therefore we can treat them as fully alive and exerting their full influence. When we do so, we remember that the corner points, the influence will be capped at 1 point, as we normally do with corridors, and we add 1 point for each stone because we're using area scoring. That yields 8 points of influence for black, minus 3 points of influence for white. That gives us 3 points net influence for black, which is precisely correct. It seems then that on the 3x3, using corridor influence with modification is a reasonable approach. The cornerstone is dead and exerts no influence whatsoever. The single stone on the side is half dead, half alive, and exerts only half influence. But if you have 2 or more of them, they are fully alive and exert their full influence. This approach yields smaller preliminary errors than the chess approach of summing the results of particular features. So what do we have so far? I think that we can generalize from the results in corridors and small rooms, as long as we remember to do so with caution and care, keeping in mind that influence depends upon the strength or how alive or dead stones actually are. Weaker stones, of course, exerting less influence. If we take this approach to estimate the value of a single stone on the board, we find that on a large board, it approaches 16 points in the limit. This would give us a comey of 8 points, which is very close to the comey that is actually in use today. As a tip, if you want to estimate the strength or the influence of a wall, for each line going out perpendicular from the wall, it sums the influence of the stones in the wall, and the influence there approaches in the limit 3.5 points. So that's not a bad rule of thumb for making that estimation. So again, results are very preliminary and a lot remains to be done, but I think we already have something that may be useful.